Good, good afternoon for the people, especially in Indonesia, and maybe good morning for the people in Europe. For example, our moderator, Dr. Nasar in UK, and also Dr. Mikael, one of the speakers in Sweden. Today, we will see the two speakers. First is Dr. Mikael in Sweden, and the last one is Professor Badesia in UK. For the first session, Dr. Nasar will help me to be the moderator of this session. So I will read just a brief introduction about Dr. Nasar. So Dr. Nasar Ali is the founder and chairman of Nanosmed, and he has held the post of a chief scientific officer at CNC Coatings Company in UK, and also he was the faculty member at the Department of Mechanical Engineering in Aveiro a few years ago, and now he is the chairman of the Nanosmed Global in UK, and Nanosmed has conducted many conference in nanoscience and nanotechnology, I think. So maybe it's a good event for Dr. Nasar Ali and maybe all of you to know about the Nanosmed and maybe about the topic from Dr. Mikael. So Dr. Nasar Ali, the screen is yours, please.
Thank you very much, Aditya, for the introduction, kind introduction, and good afternoon to you all in Indonesia, and good morning to all those who are in Europe. And I believe majority of our audience today, people are joining us probably mostly from Europe and Indonesia. And as Aditya mentioned, we had a brief sort of discussion at the beginning. During this pandemic, one of the things that we've come to sort of accept, and it's becoming more of a norm now, is to actually connect with each other on this Zoom platform. It's very, very important. And one of the things that we realize and we accept during this pandemic is that science dictates. Yes, a lot of the politicians, a lot of the world leaders, because this pandemic has actually gripped the whole world, the leaders accept that science needs to dictate. And this is, although we're not allowed or we're stopped from mixing with one another in order to stop this virus from spreading, the science must continue, the developments must continue. And this is why, we're able to use this technology, and we must continue to work together as scientists, to collaborate with one another, from different parts of Asia, from Europe, from the US. So I would like to thank Aditya for arranging these series of webinars that he's been conducting on a regular basis. And it's an honor for me to moderate this very important session. And our speaker is very, very important and well known in Europe and around the world in the work that he does. Dr. Mikael Syvvajarvi from Sweden, who's linked to the European University in Sweden. And just to sort of introduce briefly Mikael, Dr. Syvvajarvi has been active in research since 1995. Where he's looked at the growth of energy and environmental materials such as silicon carbide and graphene. And since 2005, Mikael has become very active in creating knowledge transfer to promote research and innovation to reach commercialization from research findings. He is the founder and also co-founder of several startups, communities, and networks. And in 2020, this year, he has been very active with NanoSmart, which I'm involved with, to create exchange and sharing practices in nanotechnology research and innovation. And he's given a number of webinars on this topic and has engaged also the youngsters to inspire youth to think innovatively and to be more creative. And these NanoSmart Innovation webinar series is one of the ways to create and promote learning from each other. So in such a way, more research findings may come to real use and contribute to the society. So today, Mikael will be speaking on the cross-disciplinary advanced materials research for breeding innovation and examples from metals and semiconductor avenues. So without further ado, I'll pass over to Mikael. And
Thank you very much.
I believe Mikael will speak uninterrupted for maybe 45 minutes or so, and then we will have a Q&A at the end. So if there's any questions, maybe you can just type them in the chat box, and I'm sure Mikael at the end will answer all your questions. Thank you.
Yes, thank you very much, Nazar. So I'm happy to be able to contribute to this series of presentations which you have been organizing. So this is the last one for this year. So and what I will do is that I will not go so much deep into the details of my research and what we are doing. I have done research since 1995 and done a lot of scientific studies on different topics. But what I would like to do mainly here is to encourage especially the young researchers, but all researchers in general, that when we are sharing our experiences, for example, when making startups and so on, then we can learn from each other. And particularly when it comes to advanced materials, then usually the technologies which we aim at, we cannot do the full value chain ourselves. We need to have a partnership, and then, like in Sweden, we don't have all partners in Sweden. Then we have to look internationally. That's why this exchange at conferences, but also now the webinars, is a way to find common avenues for the new things and get ideas. And like at conferences, the presentations are usually very nice, but also the time in between, when we drink coffee or have a beer in the evening and socialize, there you actually create the unexpected ideas. And some of the unexpected ideas can be quite radical new things. And I like to do more new things. And then the younger generation is much more important. I will be retired in 15, 20 years. So now the younger generation is my retirement plan. So I would like to share some of my encouragements for young people to do the new innovations, which I can use in my elderly home later on. So I will, and during this presentation, feel free to put some questions in the chat box, but also later on, you can unmute your mic and we can discuss like at the conference. So there will be a question and answer, very informal, ask anything you'd like. And now hopefully you can see my presentation. Okay, so this title is a bit complex or long. And what I will basically present is that when you are in different disciplines and you interact, there will be new ideas. And then some of those you can study more. So it's a way how to breed new innovations. And I will give some of my own examples from semiconductors, which is my main avenue. But lately also I have been come into new avenues where high temperature metallic materials and metallic alloys are combined with our type of material, ceramic silicon carbide and so on. So that became a new opportunity. So that is what I will give some examples of. And of course, the whole history until that point. So from history point of view, I started as a PhD student in 1995, so it's quite a number of years ago. And at that time, silicon carbide was a very hot topic in the research, and it started to grow really much in the 90s. And all over the world, there were a lot of researchers coming into this avenue. And that's mainly because silicon carbide is recognized as a material for power devices. So due to larger band gap and some other properties, it was very motivated that you could use this to actually replace silicon in, for example, high power devices. So the properties of silicon carbide are attractive for that. But at that time, the growth of silicon carbide was still very immature. People did not know exactly how to do. So it was a lot of fascinating things in the lab in those days. And that's how I started. And my main personal fascination is the growth of materials. And I'm not so good in calculations and so on. So I have a little bit of feeling for the growth. So that became my personal interest. That's how I came into the research of the silicon carbide. And the basic principle for the silicon carbide is that you have silicon carbide source material. So here in this schematic, you can see a source at the bottom, and that consists of silicon carbide powder, for example. And when you heat up the silicon carbide powder, then you have different vapor species which are formed. It's not silicon carbide vapor species, it's various vapor species which contain silicon and carbon. So pure silicon is one, and then you have two silicon and one carbon, and then one silicon and two carbon, and then a range of vapor species of the silicon and carbon. And those are used to being transported to the growing surface, mainly by a temperature gradient. So it's a cooler, lower temperature at the growing surface than at the source. And that is the basic sublimation type of method. Physical vapor transport is the more formal name which people are using. The PVT growth, you will be recognized. And the motivation at that time was to actually be able to grow thick bulk material of silicon carbide, and then from the bulk to cut out wafers. So you could go to the epitaxy, and from the epitaxy, you can go to the device development, and from the device, you can go into the systems and so on. So that took quite many years. So it was only maybe 5 years ago when silicon carbide became a real market with the good numbers in the financials. And until that time, it was still very much development and not very easy to find the high volume type of markets. But that is now existing. But it took like 20 years to come to that stage. And what we did was that we explored this PVT method in general. And then they made some modified approaches. And one of them is that we decreased the distance between the substrate and the source material to shorter. And then we also lowered the growth temperature. So then we could not grow the thick balls, which was the original aim, but we could use the high growth rate to grow thick layers of silicon carbide. And for the silicon carbide, when you have thick layers, when you have power devices, and if you want to transform 10,000 volt, then you need very thick layers. And that was a big challenge at that time, and still is very difficult to control very thick layers grown high growth rate. But this was a part of my PhD thesis to explore such sublimation epitaxy 4 thick layers of silicon carbide. And instead of silicon carbide powder, we were using ceramic silicon carbide as source material. So in this bottom image, the source, it is ceramic silicon carbide, which is actually possible to buy because this is used in silicon growth as dummy wafers. So for example, Mitsui has such material in wafer size. So they are grown by CVD on graphite, and then you get polycrystalline silicon carbide, a ceramic, and that is used for other purposes. But we were using it for our growth. And I will come back to this ceramic silicon carbide when it comes to another, one of the latest opportunities which we have got. So we are using such ceramic, and then the aim is to grow very thick layers. So that we managed to do. So here you see about 100 micrometer thick layer of silicon carbide. And surfaces are smooth, and if we look into the quality of the material, XRD and photoluminescence and some other things, then it shows that really it's nice quality. And that was one of the activities in my PhD thesis, which I presented in 1999. But for the power devices, this material was not useful because it was too much background doping. In the sublimation growth, you have some nitrogen and so on from the environment. So the background doping was too high for the power devices. While in CVD, you have pure gases and so on, so you can get pure layers. So the highlight of my PhD thesis was a method which was not functional for its intended use. So that was 4 years of PhD studies to that point. And then a few years later came Satoshi Kamiyama. So he proposed that let's take silicon carbide, and if we dope the material with donors and acceptors, we can get light out from silicon carbide. So silicon carbide is a light emitting material. So it's not nitrides and so on. This is silicon carbide, which is the emitting material. And for that one, he doesn't need pure layers. He wants to introduce certain dopants. So you get donors and acceptors for this luminescence. And then he needs thick layers, so you can have sufficient amount of luminescence from the layers. And then I was thinking, oh, I have a method. Let's collaborate. So then I proposed when I saw his presentation at some point many years ago. And he was visiting this university at some point. I don't remember which year. But then we started the collaboration with Mayo University on silicon carbide as a fluorescent material for light emissions towards LEDs. And that was a completely new research avenue, which was not part of any plan which I had from the beginning. I had this failed method of thick layers, and then it found its opportunity in this other application. And the basic principle here is that you have donors and acceptors. And when there's a recombination between these different levels, there is a broad range of energies. So it's not a sharp peak, it's a broad band, which is emitting from the silicon carbide. And then if you do this in 2 layers with 2 different acceptors at different level, you get 2 broad spectra. And if you do this in 6H silicon carbide, which has a band gap of 3.0 electron volts, then it comes out in the visible region. And all combined, this is then a pure white light. So this is the basic principle. And if you combine these 2 layers, one which is more warm white and one which is more blue, when you combine them, then you can get a pure white light. And this is one of the attractive features with this silicon carbide LED. And if you compare with the nitride plus phosphor LED, then you have the blue, which is converted, some part of it is converted by the phosphor, and then you have white light out. But in the very efficient LEDs, then the blue is penetrating. So you see this blue tone. And if you want to improve the light quality to more white, pure white, then you need to do compromises, filters, and so on. Then the efficiency goes down. So the silicon carbide has its unique niche. It's not super efficient, but it has this white light. So it can be finding its position once we have cleared out the physics to grow the material, understand the luminescence, and then fabricating this. And the stage we are at now is basically, we started this research some years ago, but then it was difficult to find funding and so on, so it's slow progress. But basically, these donors and acceptors, what we need to do is to find the correct amount, a concentration of these ones, and also play with the relation. And we need to do this doping in the growth without damaging the crystal quality, because that kills the luminescence and so on. So this is the stage which we have been exploring. And here you see some images. So on the left side, on the top here, you see two near UV LEDs, and they are emitting the light to the silicon carbide. And on the left side here, you see no emission at all. So the balance was not proper. And then we modified things. And then on the right side, you see that there is more luminescence. This is one of the layers. This is the warm white. There's luminescence from one of the samples. And then if we further try to optimize, we are out of the range and so on. So there is an optimum at some point where there can be luminescence from silicon carbide. And this is at room temperature. So it's not the theory, it is actually something which is happening. And what is important here is the understanding on the atomistic level. So in the background, you see a TEM image of grown material. So this was very nice quality. And there are many things which we don't understand in this research. But the good thing about not understanding is that when we try to understand, we have findings, and then we'll present it in papers and so on. So in this case, there are still many things to sort out and clear in the case of the material and how the luminescence is coming. So if you would ever like to enter a fascinating research avenue, then this is a good topic. And particularly the growth is important, and I will come back to the growth because we have these vapor species of silicon and carbon, and depending on the temperature and process and so on, what we do, then there can be different influences. So here you see a copy of some graph which we did in the beginning when we had collaboration with Mayo University, how to go up to the temperature and how long to grow. So we start the growth in a controlled way. And one of the features here is that we have the doping in the source material. And here you can see different types of source material. On the left side, you see some images before growth and after growth, and then the overall picture. And on the left image, you clearly see that it is graphitized. The whole surface is graphitized, which is very bad for the growth because then it shows that it's uncontrolled. And when we have another type of source, then it's not as much graphitized, but still it's influenced. And on the right side, you see some other type of source where it's actually not graphitized at all and so on. So this graphitization is not good from the growth point of view for the silicon carbide layers. But it is interesting from some other point of view. And if we go back to thinking about this graphitized layer, you know, the Nobel Prize for in physics 2010 was given to this gentleman for the graphene. And graphene is carbon atoms in one layer. So that led to a great scientific interest. So it was like a boom in this research of graphene. And at that time, and still, the growth is very important because we need to control the growth of the material to be able to develop the applications. So this question is the same for all new materials. And in comparison, graphene can be done either as flakes. So here is an example of when you have graphite and the Scotch tape method. When you tear down pieces and make them thinner and thinner, then at some point you will have graphene in flakes. And another method is to use metal foils, and you have a carbon containing gas, and then that one gives a carbon layer on the metal foil. And here you can come to a large area. It's still difficult to get good quality, and you need to transfer some polymer which is used for electronics and so on. And then the third method is actually coming back to the graphitization of silicon carbide. And the good thing in silicon carbide is that you have wafers which are available in large area. Today you can buy 6-inch diameter wafers. Natural process of the PVT growth and the vapor species which are formed when we heat up the silicon carbide. In the case of growth, we do this intentionally, but we can also use this to fabricate graphene. So here is an example. When we heat up the silicon carbide, you can actually get more silicon to leave the surface than the carbon of the silicon carbide wafer. So that is one way how to get graphene from the silicon carbide, and the silicon carbide is the source and substrate at the same time feature. And we have been developing this since quite many years, and around 2000 degrees C is one of the secret temperatures for this process. But actually in the silicon carbide, when we were heating up silicon carbide, but then we got this graphitization, which was not desired. But then in some collaboration with the Chalmers University, or Chalmers, Chalmers University of Technology, in that collaboration, they requested such graphitized silicon carbide to study it intentionally. And as grower, we were a little bit hesitant to do this intentionally. But then it was found out that the graphite on silicon carbide has very high quality. And when we made these thick graphitic layers thinner, then actually 2005, we had one layer of carbon on the silicon carbide. So that was a graphene. We did not understand really what it was, or what could be good for. But from the growth point of view, it was exciting to do this. And then we tried to control this, and we had some master students working on these things. And then 2010, we could control this in a nice way. And there was collaboration with Chalmers again, where they demonstrated the quantum Hall effect on our material. And it was very good quality of the material, which showed that there was, it's possible to use this for quantum resistance standards and so on. So then there was a joint paper in Nature Nanotechnology. And as a grower, it's very difficult to be in such papers because we never have device demonstrators. So this was a very nice time. So that was now 10 years ago. And the delicate thing here is that silicon carbide, when it's heated up, you have different steps. So when you have the silicon and carbon, you have bilayers, and you stack them in different ways. And then you have different surfaces. And there they can be step bunching as small steps. So this creates a problem in the growth. But this is also the way to make the graphene on silicon carbide, because it starts to grow from one edge and so on. So this surface reconstruction of silicon carbide is very important, because silicon carbide, when you heat it up, you start to have a surface reconstruction, and then the atoms start to leave, and you have the graphene and so on. And I will come back to this surface reconstruction idea in another application. But this we have studied a lot, and Professor Rosica Yakimova was my supervisor for my PhD thesis, and we have been working together since 1995, and we still do this. So then we started to explore this, and since we had very nice quality of the graphene on silicon carbide, there were more and more collaborations, and actually we could not focus on the research projects. And we were thinking, how should we do to have less requests for material? Then we actually made a startup company which asked researchers to pay for materials. So we were thinking that they would not like to pay, but then it actually became a startup, and we had sales of material from the first day. And that was at the time when my entrepreneurial interest became triggered. If we can make usefulness of the research findings, not only to produce scientific papers or make disseminations at presentation, we can actually have something which can be developed to a commercial market and used. And that's when I started to think more about this entrepreneurial path instead of the academic track. And today I'm even fully focused on this innovation and entrepreneurial things from the research. And in case of graphene on silicon carbide, these nice quality layers, they can be used for sensors and so on. So some type of electronic features for sensing. This is what we believe in can be. But it started from the unintentional graphitization of silicon carbide, and there are some sensors which have been tested over the years for this type of applications. And if we come back to this process of steps on the surface and the silicon and carbon leaving. So depending on the temperature, when you go up in temperature, there's a surface reconstruction. And then you have that more silicon is leaving the surface due to different vapor species. And then the ratio of the silicon will differ depending on the temperature. So this is not very good for the growth if there's a big unbalance in the silicon to carbon ratio. But this can also be used for making the graphene. But also here you have a surface reconstruction which is happening. And this happens on the different silicon carbide polytypes, and you have different steps. I will not, different terminations of these ones. And if we go back to this sublimation epitaxy method, where you had thick layers grown on wafers, substrates, and we were using the ceramic silicon carbide as a source. So this ceramic silicon carbide was used as a source for that one. But then we came into another avenue, because one day, maybe 2 years ago or 2.5, 3, one guy called me and said that I would like to have silicon carbide cavity where you have 2 wafers of silicon carbide and we bond them to each other in a close way. And in the center here, you have a cavity. And the idea is that we take this membrane and we place it in an engine and we explore higher temperatures than conventional, then we can save the fossil fuel. So then it becomes more efficient. And then when the engine is working, this is changing the cavity. And then they have an optical fiber which is monitoring this. And this membrane should be placed in a housing which is put into the engine. So then we came into another avenue about bonding silicon carbide at high temperature to each other. And then it should be like this silicon carbide should be single crystal because it's transparent, but this other silicon carbide should be polycrystalline ceramic because it's facing the engine, and then you have a lot of heat, and then it's actually light from the heat, which is disturbing the signal. So then we have a polycrystalline ceramic silicon carbide, which should bond it to single crystal. And this we came into, and now we are using this surface reconstruction of silicon carbide to make high temperature direct bonding. This wafer bonding has been explored before, where you have different metals in between, and then you bond them. But in this case, we want to explore the high temperature direct bonding. And that led us to another application avenue than the power devices originally. So here the automotive industry is interesting, and we have some initial research which shows that there is bonding. And other motivations is that this is not only used for the fossil fuels, this is also useful for biofuels, or in the shipping industry. Then they have big demands to reduce their emissions. So until year 2050, it should be cut down quite drastically. So this type of sensor could be used for that. And that led us to this membrane direct bonding. But also, this should be placed in a housing which is metallic alloy or something like that. So then it has to be gas tight. So the silicon carbide in connection with the metals must function together. And then I met Svetlana Stekovic, who is exploring high temperature metallic alloys for aerospace. So she is a coordinator of 2 Clean Sky projects for the high temperature metallic alloys and high temperature materials. So then we started to discuss these things, and then we applied for some pre-studies. So then our different expertise is from completely different avenues, still materials, but in my case it was semiconductors, and she is in the high temperature metallic alloys for aerospace. And then they're studying how this material can work at high temperatures and so on. So that led us to a new collaboration, and we have a couple of pre-studies to build up this new research avenue. So maybe in the future, our interest will be very much into this combination of the ceramic silicon carbide with the metallic materials. This was one application, but maybe there are other ones where this combination can be unique. And then I think probably high temperature applications are something which is very attractive. So I'm not a metallic researcher yet, but these natural different backgrounds, and when we meet people and discuss, then it opens new opportunities. And this guy who called me, he did not just know about me, but when I've been doing dissemination to media and releasing some information that we have silicon carbide growth, then he saw that at some point. Then he was thinking I should call that guy, and one day he called, and then we discussed these things, and then the projects led. So this is why I think it's so useful to actually be open with the information, what type of research we are doing, and disseminate not only at conferences but also to the general public. And this type of webinars are super excellent because anyone can participate and get some ideas and then propose, maybe we should discuss these things. So in that case, this avenue could be something which is possible to study more in the future, and to end up with what is happening, because it's not just to explore the research and then use it in an application and then you have a market. If we look into the LED, for example, then the first findings were done many years ago, 70s, 80s, about the material, and then you had all these different developments. So Professor Amano was giving a talk at European MRS, and then that first development took 30 years, and now the funding agencies would like to have similar revolutionary technology.
Ini ngajakin orang kantor teman.
Like the LED, but it should not be 30 years, it should be
Kan
less.
harus daftar, kan baru dikasih tahu.
So maybe I could ask some of the participants to mute their microphones. Thank you. So then the funding agency would like to have these revolutionary technologies in less than 10 years, they say. But then it's not possible, Professor Amano said, but maybe we can find some ways how to facilitate this more. So in Japan, students who would like to become entrepreneurs, they are encouraged to do these things. And when you have research findings, which should be reproducible into production, there are also students who are interested in that. So then they're also encouraged, And in case there are new technologies, those students who invent new technologies, they should also be encouraged. And overall, there are mentorship program, internship, just to facilitate that this happens more systematically. And also in Europe, this is happening because we have the European Commission has programs for how the regions should do more economic growth. And regions are doing more economic growth when they find value chains in a certain topic where there are many actors from the same region or collaboration regions. So they focus to encourage that. And at the end, it's a value chain which is identified. And in the research, what we're doing is that we're proposing we do this and we are using this and it should go to this stage. So it's also a value chain. So if these two interact more, there will be more usefulness from the research. And if we as researchers can a little bit understand more that this is actually existing, then we can motivate ourselves much more. And when we apply for fundings and so on, then we can show that this is relevant for our region or so on. So then we find more motivations than the incremental step of technology improvement. And I know a little bit about these things because I was involved in our region's working group, which built up this. So that's why I came into this activity, and I know a little bit about it. And what will happen is that you have people who know things, and when there's exchange, more things are happening and more ideas. And in some cases, it will be relevant on regional level. And over time, this happens in Europe, but over time, when you have the regional exchanges, next, when we need a partner in some technology, it will be international partner. So someone has expertise somewhere which is needed for this value chain. So that's why international partnerships will be more and more important. And these things are nice, and the motivations on the regional level, higher level are nice, but at the end, we need some pilot projects. So the ideas in the lab are super important. So when we discuss the things in the lab or together like this at the webinar and sharing experiences and thinkings and thoughts, then we create some new things. So this is one of my things which I'm trying to do more and more, to encourage, actually test things, be open with other people. And over time, the motivations, like in my case, we focus on energy and environmental materials, either sensors or LEDs or solar cells, based on silicon carbide ideas. This is my unique positioning. And over time, maybe we can contribute with some of the technologies which can be promoting that there is a change from our generation to the young generation, which is happening. So with this, I hope I have given you some sharing of my experiences about how things have occurred and done. And it was not the plan from the beginning to go into these different avenues, but it just emerged because there was interaction between people. And that's also why I think these digital meetings are super fantastic, because then we don't need to travel to go to a conference, so we can do more of these things and exchange ideas and have a discussion like this. And it is at least a little bit personal because we have the video, so we can see some face and not only presentation. So those things are very useful for the future. So this is what I believe we can do more of. So I'm very happy that now I was invited to make a presentation in Indonesia. This is my first time in Indonesia, but I'm sitting in Sweden. But at some point, I hope to come and visit, and we can discuss some other ideas. So thank you very much.
Okay. Thank you very much, Mikael, for an excellent presentation, very enlightening. I see we have about 91 people who joined this meeting, so I'm sure there's going to be plenty of questions. So do we anyone with a question? Maybe if you could just unmute yourself and ask Mikael the question.
There is one question in the chat box.
Yeah.
So,
yeah.
AFM characterization, yes, we are doing that a lot, especially to understand the steps when we have them, because the steps vary in how they look like depending on the growth parameters and processes, and preferably they should be as small as possible and straight, because we are growing step by step of the layers. But when there are step bunchings, then those also start to deviate and so on, which is not so good from the growth point of view. But also what this can be used for is to actually intentionally create steps. And then, like when we are doing graphene, we can also get nanoribbon graphene along the steps and so on. So the AFM characterization is very useful for the surface processes.
I think the second question was, what was the cause of the fracture?
I'm not sure I understand what is the fracture meaning.
Maybe from the research result with your partner, when you combine this silicon carbide with the metallic alloy. There is
yes. Okay. Yeah. In that one, there is. For example, in the high temperature metallic alloys, when you're using these in aerospace and, for example, engines, then there's a lot of variations and so on. And like in this membrane, what will happen is that you go from minus 40 degrees Celsius to 800, and this is done many times. And then the sensor should function over long time, because you don't want to change the sensor in the housing of an engine. So then fracture is how to understand when we test materials which we have been fabricating or in combination, how do fractures and other mechanisms which are destructive for the material, how do they occur? Maybe we can modify the process in some way. So there are causes, but since we are at very early stage, we don't know this in this case. And Svetlana's research, and there they know more, but I'm not expert in the metallic alloys. But this is certainly an avenue where we need to know more when we are looking into these new applications.
Okay. Any other questions? Do you have any questions for Mikael?
Yes. I have question. Mr. Nazar,
Yes, feel free to ask
Hello?
question directly.
Yeah, please ask.
Yes, my question is, if the silicon carbide is already mass production. Secondly, if they compare with titanium base and aluminum base, which the best for the property, like mechanical, physical, and microstructure also. Thank you.
Yes, now it was a little bit poor signal, so I could not hear the whole question.
Yeah.
But from the property point of view,
sorry,
it depends on the application.
Maybe I can help Pak Agus. Apa pertanyaannya?
Yes. Yes, the question is, this material silicon carbide already mass production in the world. And secondly, if they compare with the titanium and aluminum base, titanium carbide and aluminum carbide, Which is the best
Sorry,
for the
Mr. Agus, because the quality of your connection is not really good. Please write it down in the chat box for the question, because we cannot hear clearly your
clearly,
question.
yeah. Okay.
Okay, I think there's a question in the chat box, and the question is that is there any effect from high temperature process on the microstructure or grain properties? Because in nanocrystalline materials, we have significant grain size at the elevated temperature.
Yes, there would be an effect. And now we have not studied this so much, so we actually know many of the details. But the good thing here is that ceramic silicon carbide, which we are using, it's very dense. So it's a high density material, so it's almost like single crystal. So the density is very high. This means that also the grains are not affected to a large extent in the initial process. And we are not exposing these materials for a long time because we want to have a arrangement of the surface so they are bonded, and that is not many hours. It's a matter of minutes or tens of minutes depending on conditions when these things are happening. So then the bulk of the ceramic silicon carbide is not influenced. But this is also something which I'm interested in. Could we use our high temperature processing, for example, to modify porous silicon and carbon type of materials, and then, for example, to make more porosity or increase the grains in such type of material? And why I'm thinking of this is that we have very much expertise in high temperature heating, so there's a lot of tricks there. And single crystal material applications, that's more difficult to get fundings, and we would like to go into new avenues. But I know, for example, that the silicon carbide is used for water cleaning, and then you have pores in the material, which is used for the cleaning of water from some elements and so on. So maybe we can use this grain coarsening effect in silicon carbide for such type of applications using high temperature. But we have not studied that too so much in detail because we come from the single crystal world, and these are new avenues which we would like to. So it's a very good question because it triggers the ideas and thinking ahead or possible collaborations. So.
Did you also try to grow graphene on silicon carbide?
Yeah, on the single crystal we have been growing, like I showed, we have the graphene on the single crystal which we had, but then we're also trying to grow 2 layers, 3 layers, 4 layers, because then you have a little bit shift of properties from the monolayer graphene. And maybe at some point, maybe the graphitic layers is the one which is interesting for some type of application.
So what was that kind of a CVD process? Or
no, this is the sublimation which I presented. When we heat up the silicon carbide, then silicon is leaving the surface, and then we don't need any external gases and so on, like the CVD. Mm-hmm. If you have a CVD process, you have some benefits, but also from infrastructure point of view, then you need, when you build a lab or a fab later on, then the cost of the gases is very expensive. So I would prefer not to need any gases like in the CVD, because if we can use the natural habit of silicon carbide, the sublimation of the material, then we are it will be unique in some way. We cannot do everything, but it's a unique possibility.
Okay. You have any other questions for Mikael?
I can also try to answer Dr. Sotisna's question. because there we don't have comparison with the other materials like this aluminum, carbon, and so on. So we don't know which is better, and then it depends on applications and so on. But the good thing is that if we find, yes, here, because in the question there is also silicon carbide, since this is now mass produced, both on wafer level, but also since many years, there is powder which is mass produced for other applications like polishing and grinding. Then there is mass production of silicon carbide. And the good thing is that when there is mass production of these things for other purposes, it means that the cost of material is lowered. So if we have additional applications, then we don't need to lower the cost of material because that is done already for other purposes. And one example which I take is that, for example, the silicon solar cells, they would have never been developed if it was not for the motivation of silicon in the transistor. So the transistor development lowered the cost of silicon, and then the solar application could tag along. But from the beginning, it was not financially motivated to develop the solar. Here we can do something similar with silicon carbide, that it is now commercial market and prices are going down because there are higher volumes. So if we find some unique application, it can actually be financially viable already now. So that's why new ideas are possible.
Okay, thank you very much, Mikael. Excellent presentation. I think we do have a last question. How to predict the lifetime in high temperature component application, i.e. for material with barrier coating? And if I use Larsen-Miller parameter based on homologous temperature for specific alloy?
Oh, yes, that's thank you for the question. This is not my area of expertise, but for example, what is done is that there is, when we test the materials in the lab at some point, we can stress them a little bit more than what is used in the application. So for example, if we do recycling from low to high temperature, we can do this over some time and stress it a little bit more. And then we can expect, then we can make an estimation from the failure of this, that when we go to more safe, then it should be at least longer than that. So I think that is how things are done. And the good thing about working with people from the aerospace is that they are doing these things for aerospace materials, and no one will ever allow to use material in the aerospace because it's a safety issue. So there's a lot of competence in estimating and making various types of tests and put it together to make an educated guess on how long is the lifetime. So we can use that experience from this other discipline also for these new things. And also I'm interested in the combination, like Agus is asking, if silicon carbide is used with titanium and aluminum. Yeah, there are such combinations, and I think we can combine those things in a nice way. And we have another project which is focusing on titanium nitride, and there I think the titanium nitride, which has some benefit, in combination with silicon carbide can also be some new avenues and so on, but maybe not a mix of all these things in one, or maybe we need a mix to some extent so it matches better with, for example, pure silicon carbide or the ceramic silicon carbide, depending on the application. So there are many things here which we don't know because it's new avenues, but certainly all these ideas are worthwhile thinking about, because then maybe it motivates a new application which was not known before. And now when we have various needs to create more usefulness and save energy and so on. And so on. Then there can be some super unique things which are related to this type of questions.
Okay, thank you very much, Mikael. I know there's probably a lot more questions as well, because a lot of people have started to join us, but we have gone over our time now, and I know that there's another webinar as well. So I think what we could do is, maybe, I'm sure there's a lot of discussions and a lot of sort of questions for Mikael. Maybe if Mikael could leave his email in the chat box, and people could sort of get in contact with him in order to work together and create new partnerships with European partners to overcome some of the scientific challenges. So I'd like to just thank everyone for joining us, and I'm sure you found the webinar very useful, and I'm sure you will continue to sort of with any discussions that you want to follow with Mikael. And I do see we have our next Professor Hari Badashi here with us as well. He's about to give his webinar. So once again, thank you very much for your attention, and we look forward to the next webinar. Over to you, Aditya.